In April 1942, within the fortified walls of Combined Operations Headquarters in London, a question was posed that seemed to defy the laws of physics and the harsh realities of naval warfare. Vice Admiral Lord Louis Mountbatten, a man known for his aggressive and often unorthodox approach to warfare, turned to Geoffrey Lloyd, the Secretary for Petroleum, with a proposition that would alter the course of history. The question was deceptively simple. Could an oil pipeline be laid across the floor of the English Channel to fuel an invasion of Europe? To the experts in the room, the men who understood the crushing pressure of the deep and the violent currents of the Channel, the idea was ludicrous. Brigadier Sir Donald Banks, of the Petroleum Warfare Department, consulted his engineers and delivered a verdict that was as swift as it was discouraging. They declared it impossible. The consensus was that no pipe with a diameter larger than 6 inches could possibly withstand the combination of internal pressure, tidal force, and its own weight without fracturing. In the spring of 1942, with the Allies on the back foot and the continent of Europe firmly under the boot of the Third Reich, the concept was dismissed as a fantasy. Yet, 3 years later, the impossible had become routine. By the time the Allied armies were surging across the Rhine into the heart of Germany, British engineers were pumping millions of gallons of fuel beneath the very waters that had once been deemed an insurmountable barrier. A network of pipelines stretched 70 nautical miles from the Isle of Wight to Cherbourg and 30 miles from Dungeness to Boulogne, silently feeding the war machine. 500 miles of pipe lay on the seabed, invisible and unstoppable. By March 1945, these arteries of victory were delivering over 1 million gallons of fuel every single day, enough to power thousands of tanks, tens of thousands of support vehicles, and an entire mechanized army. What makes this feat even more extraordinary is the total blindness of the enemy. German intelligence, usually renowned for its efficiency and ruthlessness, never detected the construction, never spotted the deployment, and remained oblivious during 9 months of continuous operation. They never saw the pumping stations capable of delivering nearly 4,000 tons of fuel a day because the pipelines that helped when the war remained invisible to the enemy watching from across the Channel. To understand the magnitude of this engineering miracle, one must first understand the logistical nightmare that haunted Allied planners as they looked toward the liberation of France. By June 1944, the strategists for Operation Overlord were staring at a mathematical impossibility. The invasion plan called for landing 156,000 men on the beaches of Normandy within the first 24 hours. This human wave was merely the tip of the spear. The real challenge lay in sustaining them. Each infantry division required 800 tons of supplies daily to remain combative. Armored divisions, the steel fists of the Allied advance, required twice that amount. The fuel consumption alone was staggering. A single Sherman tank, the workhorse of the American and British armored units, burned 1 gallon of fuel for every mile it traveled. When multiplied by thousands of vehicles including aircraft, trucks, generators, and landing craft, the numbers became overwhelming. The standard supply methods of the time simply could not cope with such voracious demand. The traditional logic of warfare dictated that tankers would deliver fuel to functioning ports, where it would be offloaded into storage tanks and then distributed by truck. However, Normandy possessed no such ports. Cherbourg, the nearest major harbor, was heavily fortified and would not fall to the Allies until late June. And even then, it would be thoroughly sabotaged by retreating German forces. The Allies had a solution for cargo in the form of the artificial Mulberry harbors, but these engineering marvels lacked dedicated bulk fuel facilities. Every gallon of petrol had to cross the beach in containers, a process that was inefficient and dangerous. The British relied on 5-gallon petrol tins, which were notoriously flimsy. Up to 1/3 of their contents would often leak away before reaching the front lines, turning supply depots into fire hazards. The American jerry cans were superior in design but scarce in number. The U.S. Army had stockpiled 12 million of them before D-Day, yet by October, 3.5 million had vanished, scattered in a trail of discarded metal from Normandy to the West Wall. The congestion on the beaches became critical. Supply ships waited days to unload their cargo, sitting ducks for German artillery or the remaining Luftwaffe bombers. Once ashore, fuel sat in dumps that were vulnerable to sabotage and enemy fire. Furthermore, the very act of transporting fuel consumed fuel. A truck convoy traveling from the depots in Cherbourg to the front lines burned 1 gallon of gasoline for every 5 gallons it delivered to the combat units. This was a logistical loop of diminishing returns that threatened to stall the Allied advance just as it gathered momentum. German field commanders understood this vulnerability perfectly. They had seen the same dynamics play out in North Africa, Sicily, and Italy. Their doctrine was simple: destroy the ports and sink the tankers, and the invasion would fail. They assumed that the Allied supply chain would follow conventional patterns: tankers to ports, ports to trucks, trucks to tanks. Disrupt any link in that chain, and the entire system collapses. What they did not foresee was that the British would bypass the chain entirely. The breakthrough that saved the invasion originated from the mind of Arthur Clifford Hartley, the chief engineer of the Anglo-Iranian Oil Company. On April 15, 1942, Hartley was present at the meeting where Mountbatten's impossible question was raised. While the other experts shook their heads, Hartley saw a possibility. His confidence was born of experience. He had spent years in the harsh terrain of Iran, operating hypershare pipelines. His company ran a 3-inch pipeline at 1,500 pounds per square inch, delivering 100,000 imperial gallons daily across deserts, mountains, and rivers. Hartley reasoned that if a pipe could cross the Zagros Mountains, it could cross the English Channel. The primary obstacle was not pressure, as the other engineers feared, but flexibility. A rigid steel pipe laid on the seabed would be subjected to immense stress. Ocean currents would bend it, the uneven ocean floor would crack it, and a ship's anchor dragging across it would shatter it. Hartley proposed a radical shift in perspective. Instead of thinking like pipeline engineers, they needed to think like cable layers. Britain had been the undisputed master of submarine telegraph cables since 1850. By 1880, the world's oceans were crisscrossed by 90,000 miles of cable, the vast majority of it British. Hartley's insight was elegantly simple. If one removed the copper core of a telegraph cable and kept the armored, flexible outer construction, the result would be a hollow, pressure-resistant tube that could be spooled and laid exactly like a cable. This idea birthed two parallel designs that would compete to solve the problem. The first was the Heiss pipeline, an acronym for Hartley, Anglo-Iranian, and Siemens Brothers. The second was the Hamel pipeline, named for the engineers Hammock and Ellis. Both aimed to solve the same problem, but through vastly different engineering philosophies. The Heiss design was a masterpiece of adaptation. It began with a 3-inch bore lead tube, chosen for its flexibility and resistance to corrosion. This core was wrapped in a petroleum residue compound for waterproofing, followed by layers of paper, tape, and cotton tape, to provide the necessary strength to withstand the internal pressure of fuel. 4 layers of steel strip armor were wound around the core. This was covered with jute yarn and finished with 57 galvanized steel wires wound in a heavy armor. The resulting pipe had an external diameter of 4.5 inches and weighed 55 long tons per nautical mile when filled with fuel. It was tested to destruction at pressures exceeding 4,000 pounds per square inch, far beyond the operational requirement. The construction was identical to the submarine telegraph cables that Siemens Brothers of Woolwich had been manufacturing since 1863. They possessed the unique knowledge of how to make flexible tubes that could withstand crushing depths and resist the gnawing salt of the ocean. This was a uniquely British advantage. No other nation on Earth possessed this specific combination of petroleum engineering and deep-sea cable technology. The rival Hamel design took a utilitarian path, driven by the scarcity of lead. It utilized standard mild steel pipe, 3.5 inches in diameter, produced in 40-foot sections by Stewart's and Lloyd's of Corby. These sections were flash-welded together to create continuous links. It was simpler and cheaper than the Heiss cable, but it lacked the armored protection and intrinsic flexibility of its rival. Both designs, however, faced the same deployment problem: how to get miles of heavy pipe onto the seabed without kinking or breaking it. The solution for the rigid Hamel pipe was the conundrum, a floating drum of colossal proportions, 30 to 40 feet in diameter and 60 feet long. The conundrum weighed 250 tons empty. When fully loaded with 60 nautical miles of steel pipe, it weighed 1,600 tons. It was designed to be towed by 3 powerful tugboats. As the drum moved forward through the water, it rotated, unwinding the pipe directly onto the seabed like a giant spool of thread. There was no need for complex machinery. The motion of the drum did the work. Secrecy was the paramount concern. The project was given the codename PLUTO, for pipelines under the ocean, and the operational details were hidden behind a wall of Disney-themed nomenclature. The route to Cherbourg was dubbed Bambi, while the route to Boulogne became DUMBO. The word pipeline was strictly forbidden. All personnel were instructed to refer to the equipment as cables. Even the delivery drivers involved in the logistics were kept in the dark, required to telephone from public call boxes for instructions to prevent interception. Locations were erased from maps, and records were sealed. This obsession with security extended to the highest levels of the Allied command, and for good reason. If the Germans realized the Allies were building a permanent fuel link, they would have directed every available U-boat and bomber to destroy it. The testing phase was fraught with failure and frustration, a testament to the difficulty of the task. The first prototype laid across the River Medway in May 1942 failed within 2 days when the lead extruded under pressure. But the engineers persisted. By December 1942, a full-scale test across the Bristol Channel proved that the system worked. Production ramped up, involving British manufacturers like Siemens Brothers, Henleys, and Glovers, alongside American giants like Phelps, Dodge, and General Electric. Yet the first attempt to cross the channel on August 12, 1944, ended in disaster. The HMS Latimer laid the Heiss pipeline successfully to the French coast, only for an escort destroyer to accidentally snag the line with its anchor during night maneuvers, severing millions of pounds of engineering in an instant. Subsequent attempts were plagued by bad luck. propellers cut lines, and the massive conundrum drums seized up when barnacles clogged their mechanisms, success finally arrived in late September 1944. A heist cable began pumping fuel from the Isle of Wight to Cherbourg, delivering 56,000 imperial gallons per day to the American forces. However, the Bambi route proved too long and vulnerable to the rough waters of the open channel, and it was abandoned in early October. The real triumph was the Dumbo route. In late October, a shorter, more protected line was laid from Dungeness to Boulogne. Pumping began immediately, and this time, the lines held. As the Allied armies pushed east, the pipelines followed. By early 1945, 17 pipelines were operational, and daily delivery reached 1,300 long tons. The most remarkable aspect of PLUTO was the total intelligence failure of the German High Command. Archives examined after the war contained no intelligence reports mentioning Allied cross-channel pipelines. No Luftwaffe reconnaissance identified the installations. No U-boat reported suspicious cable laying, and no spy network detected the massive industrial effort. This blindness was caused by a combination of Allied air supremacy, which prevented German aircraft from taking higher resolution photos, and brilliant camouflage. The British double-cross system had turned every German agent in Britain, feeding the Abwehr false information. Meanwhile, the physical concealment was ingenious. Pumping stations were disguised as seaside bungalows, complete with fake windows and gardens. One station operated out of a building masquerading as Brown's ice cream shop. Another hid inside a garage, and a third was concealed in a gravel pit. From the air, the storage tanks looked like innocent farm buildings or fields, covered in camouflage material to further confuse the enemy. A massive deception operation was staged at Dover. Architect Basil Spence designed a fake oil dock covering 3 acres, complete with scaffolding, fiberboard structures, and old sewage pipes painted to look like oil lines. Wind machines were used to create dust clouds, simulating constant activity. King George VI even inspected the fake site to lend it credibility. German reconnaissance planes photographed the Dover site extensively, and analysts reported a major oil facility there. Meanwhile, 30 miles away at Dungeness, the real fuel was flowing beneath the notice of the world, disguised as a sleepy seaside village, while the pipelines contributed only a small percentage of total fuel. During the initial Normandy campaign, their value skyrocketed as the war entered its final, decisive phase. By the spring of 1945, PLUTO was delivering close to 1 million gallons daily, relieving the strain on the exhausted truck drivers of the Red Ball Express. British pipelines eliminated thousands of dangerous truck journeys, freeing up vehicles for other cargo and reducing the vulnerability of the supply chain to weather and mechanical failure. In stark contrast, the German war machine was grinding to a halt due to a lack of fuel. During the Battle of the Bulge, the German offensive failed in large part because their tanks ran dry. They were forced to rely on rail and road transport that was being decimated by Allied bombing. While American soldiers were creating walls of fire to deny Germans access to fuel dumps, Allied fuel was flowing silently and continuously through underwater pipes that were immune to interdiction. The legacy of PLUTO extended far beyond the war. It was a victory of British engineering ingenuity, leveraging a unique national history of submarine cable maintenance to solve a thoroughly modern military problem. German engineers, despite their prowess in rocketry and jet engines, lacked this specific maritime tradition and thus never imagined such a solution was possible. They looked for tankers and trucks because that was the only way they knew how to move fuel. The British, faced with an impossible question, invented a new answer. The technology developed for PLUTO laid the groundwork for the modern offshore oil industry, proving that pipelines could be laid and maintained in deep water. Yet the true marvel remains the silence. For 3 years, thousands of people worked on a project of massive scale, hiding it in plain sight, until the fuel that powered the final victory flowed through the veins of a system the enemy never knew existed.